No, you just don't, you have any other information. That's all you know, okay? Yeah.
The number of times y is explained by x, that is.
You tell the full part, okay? All of it, yes.
So 1 unit change, how many times 1 unit? 1 unit change in y.
And what is that? Okay.
I mean the slope which you.
Yeah, so can you tell without using any other language, okay? Just tell me in a plain English language that his question is that the question you were asking? That you want to know that, he wants to know that, okay, I've got this result. I want to know that I'm only interested in x1 because that's all I care about. How x1 is impacting y. The results here. I'm asking you, can you help him? No. No, it's not my question. Okay, it is his question. Okay. Okay. Yeah. Okay. Linear. It's a linear. In x1 will change y by beta 1. If beta 1 is positive, it will positive. It's negative. I'm saying it's a beta. Is the value of beta 1. Did you get your answer, sir? Okay. And there is no indirect or more complicated stuff. It's a very simple linear regression. That is of beta. If you think of the beta, does not matter. You should not worry about it because that's a very fundamental thing. Okay, what is the because now we are going to get into nonlinear model. Okay, the linear model interpretation was straightforward. Okay, in the nonlinear model, it's not straightforward. So now we are getting into more complicated stuff without knowing the very basic things, which is taught in the first chapter in the first year. Okay, now we are doing PhD. We have to be very, very careful about these kind of stuff. So we have a dependent variable, and it has two states. Okay? Let's say it has a outcome, which we can say representing with 0, a variable taking two values. Okay? It's taking 0, and let's say it is taking 1. Okay? So now it is the dependent variable is a restricted variable. Okay? Now we make all those linear regression analysis, the assumptions of normal distribution of y and all of that. So this is not that kind of restricted range. It has only two values, the first one. Okay? The second value doesn't necessarily have to be 1. It could be any other positive number, and it will still give you the same kind of result. It's just the tradition. People use 0 and 1. Okay? And it will still give you, the meaning is still the same. So now the question is that we want to know the impact of x1 on y. Okay? That how x1 is going to impact the y. So now we cannot model it using the linear regression framework. Okay? So here it becomes a little bit more complicated. So we are modeling it using that, okay, what is the probability of an event? So it's like having a negative outcome or a positive outcome. So negative outcome could be like a death, for example. And it's negative, but from this perspective, it's actually the positive one because it's taking the value 1. Okay? The occurrence of death versus not occurring a death. Okay? Having an accident or not, buying an insurance or not buying an insurance. So any variable, and we are trying to predict that, okay, if something x1 changes, how your probability of buying an insurance changes, or if somebody is taking a medicine, okay, you want to know that, okay, whether this medicine is effective. So you are looking at, okay, if the patients take this medicine, whether the probability of death will go down or something will change or it's not, okay, or how it is changing. Okay? So in order to do that, we model it using a probability distribution here, which is the exponential of the x beta. So it's just the matrix form. Okay? So all the x variables are being represented divided by 1 plus e to the power x of beta. So this is the probability of taking the value of 1. Okay? So what is the probability? And we are referring that with a p here, representing the probability that y will be 1. What is the probability of y becoming the 1? Okay? So that's the expression it is going to take. Now, if you look at, and if you do some little bit of math, okay? So here we will modify this basic expression, and then it can be transformed into a more simpler one, that the log of p is the probability of y becoming 1, okay, divided by 1 minus the p is still the probability of y becoming the 1, is equal to the x beta. Okay? So now you can see the right hand side of this equation, y is equal to, let's say, xb plus c, okay, the constant, okay, in a linear regression framework. Okay? Now we're doing a little bit of the math on this. The right similar to what it looks like in a linear regression framework, but the left side is kind of now different. Okay? It's not y, but it is the probability of y becoming 1, and then the probability of that divided by 1 minus p and log of that. So it's a little bit more kind of complicated stuff. Now here the answer is not straightforward, but it has a special meaning. Okay? So if the probability of something happening is p, and there are only 2 states, okay? Let's say you're tossing a coin, okay? It can either be like head or tail. So it has only 2 possible outcomes. If the probability of occurring that event is p, what is the probability of not occurring that event? 1 minus p, okay? So now you can see that what it is telling us is the ratio of the probability of occurring that event divided by the probability of not occurring that event, and we are getting the log of that. Okay? So it is called the odds ratio. Okay? The it's part of that family. Okay? But I'll tell you. So I'm just saying you that if it follows, okay, distribution, because there are only 2 events, 2 states, then what I'm explaining you that, okay, get into this form, okay, and okay, what you see in the middle is actually the odds ratio, okay, which is the log of odds ratio is equal to xb, which is, we are very familiar with this part. Okay, the right hand side is the same. We just now made simpler so it's essentially the log of odds equal to xb. Now there is which is called a so we call it a logistic regression. Yeah, it has 2 states. Okay, so that's where trying to, yes, yes, yeah, we are looking at that situation, and we will look at when there are more possibilities. Okay, so there are some additional possibilities. So this is the situation we are looking at. There are, like, you're looking at, okay, somebody dying, somebody doing something or not doing something, somebody failing in a class. Yeah, that's where it is. So we are looking at the probability of So this is why it's okay. So that's the beginning. Okay, we have a variable that has only two states. Okay, so that's from the very definition, because we started with that kind of a variable. We are facing a situation where the situation that we want to model is this, that it can take only two. Okay, so we are looking at somebody, let's say, failing a class or not failing the class. Obviously, it's a possible that, okay, you can look at the grade, like whether somebody get an A or B or this percentage or that percent. But let's say somebody is only interested in that, okay, I want to model whether a given student is likely to fail or not fail. Okay, the situation is the variable of interest, the phenomenon of interest is that what is the probability of some students failing the class. Okay? That's what we want to model. Or we're looking at a medicine, so it can be could be intermediate stages. But the one that is of interest is that, okay, whether some person is going to like die or not, you are going to somebody is going to like get an accident or not. Okay, so it's just two. Either you got it or you didn't get it. Okay, like those kind of things. So the situation is there were only two possibilities. The dependent variable is a restricted dependent variable. It can take only two values. One is, let's say, 0. And the other is another positive number, which we are calling here is a 1. Okay? Just saying the two states. And we are trying to model that, how we are going to model that. So we call, and you here, that was the initial expression, that what is the probability of a y occurring 1 given the x will be, this is the probability, which translates into a very kind of intuitive interpretation of this, which is the log equal to x beta. Now, we call this model a logistic regression model. Okay? So, can you see this better a little bit? Okay. So, what I did, I'm still using the same data set that we have, okay, so that it becomes easy rather than kind of getting another. We're just trying to create a variable that can take only two values. In that data set, we had a variable which was innovative, innovation 1, okay? And it was a count variable. It had the values from maybe from 4 or 5 to 20 or 21, okay? But it was, by design, I had a variable in the model which was a count, integer variable, okay? It could take only the integer values. Now I am taking that variable and actually forcing it, creating a new variable that can take only two values, okay? Because I needed one. Okay? So I'm looking for one, so I'm just forcing it. So I created a new one, recoded. So I've recoded, okay, if from 1 to 15, I call it 0. And if it was more than 15, from beginning from 16 to whatever the maximum value was, became 1. Okay? And I just gave a name to that, okay? Because the first one was how many pretended, okay, innovations or patents the company had done. So this one, I kind of created it, said that, okay, if it was less than 15 or up to 15, you are not innovative, okay? And if you had higher than that, I'm calling it that you are innovative, okay? So now there is a meaning of that variable, just giving it, okay? So we created a variable, a firm could be innovative or not innovative, okay? And now our job is to predict that what is the probability of a company becoming innovative as a function of some of the variables we will look at. Okay? That's the problem we are trying to look at. And it could be anything, it's just a made up thing. Okay? If you associate with some other context, just make your own context. Okay? Because this is what we're just looking at a variable, that dichotomous variable. It is taking two states, and we're trying to predict, okay, what is the probability of it taking a positive state. So I did it just as part of that, it was done or not, right? Okay. See that we did just inspect, okay? So this is the recode command, right? Recode command is, so there was innovation variable 1 was already there in the data set, in the original data set that we created. Now we are creating a new variable, okay? So the new variable is based on recoding the information here and generating a new variable which was innovative, okay? And it is done by recoding. And how the recoding is done? The scheme is that, okay, from 1 to 15, it will become 0. And anything above 15 will become 1. Now we got a dichotomous variable. We gave it a name, innovative. Now we are inspecting just to make sure that this is what we did. Okay. So I did the inspect, and we did the inspect. We saw that okay, this variable inspect innovative, it takes only 2 values. Okay. So it is wanted. That's what we're trying to do. So we got that. The second part, it is also giving me some more number. Okay. Then 36 zeros and uh, 164 observations for which this variable has positive value, and 10,636 it has a negative. I could have changed the level, okay, 15, you could make 10, 15, whatever. Okay? It's a random thing. Okay? We are just trying to make a data set, create a situation. I needed a dichotomous variable, and we're just doing it. Okay? And it could be, the choice does not matter. Okay? You can change the choice as you change the cutoff, it will,
How do we get the credit?
no, this is, we are creating a data for an example. Okay? Are going to measure, okay, the people who them one, okay, the people who are still alive, you're coding them as you have people who are tracing them, okay, so you're not making it up, okay, so the only way is that people, you need to know that, okay, how many people had accidents, okay? So you need people either tell you that, yes, I have an accident, or so let's say we're using 1 year, okay? If they say yes, if they said that no, I said, okay, 0, okay? So that's your data set you are building. Looking at is, it has only 2 states, okay? It happened, you are just coding it if it happened, giving it 1 or whatever, and if it did not happen, it's 0. See, if you do that, people will be really mad at you, okay? You have a more fine-grained information, why you are losing and dichotomizing the information, okay? So you have an observation, you said performance, okay? You're looking at export performance, so you have many observations, more fine-grained observations. So why would you actually take that fine-grained information and make it a dichotomous one? That's the first part, okay? It's your call, you or the researchers, you have to tell data. I creating one. It's not, I am trying to produce. Trying to predict that whether this diet plan has an impact on people becoming fat or thin. Okay? You decide what you mean by fat. Okay? People, you have the data, you have got the weight, everyone. I'm not the one who is going to tell, okay, what is the criteria cutoff, at what point would you consider that's a fact? Okay, this person is fat. Let's say that's what you're trying to do. Make sense? Now? Yeah. So the weight is a continuous variable, but you are interested in saying that, okay, what is the probability of somebody becoming fat? So now you need a cutoff that, okay, maybe body mass index or whatever, something. You need to know what it is, okay? At what point? And the 50. Right, this is just an example, okay? Don't try to go and just put 15 in your variable and say that, oh, I did 15 because in my class the professor was doing 15. Oh my goodness, I did 15 because it's just a number, random number, okay? You guys did the same thing. With the first day, I spent 1 hour. You couldn't open a folder. Why? Because you're typing MK Srivastava in your path name. That's my name. Your name, sir. Come on, give me a break. I'm showing you that here is my address. This is how to write your address. And you're writing your address on your envelope, my address, and saying that, oh, this didn't go to my home. Yeah, because you put my address on that. I was asking you, I was giving an example that this is how to write an address, sir. Follow it? Yeah. Great. But so this is just an example. This is just I had to create a situation. And we are just creating. I didn't need to borrow a data from outside because we can build it. We can create what we need and then run all the results, all the models, so the goal is to learn the technique. Have the data which meets, and then let's model it. To go about modeling it. Okay, so this whole slide was just, remember, it's making a situation. It says the 15 is just a number. I had information, I thought, okay, I just changed it, okay? You made my day, okay? Because if you were going in your data and you did 15, and then somebody said, where is the 15 coming? Oh, I did a GIAN workshop. And in that workshop, the professor was telling 2 to 15, and that's why I did it 15. So when we were in college, we were at like a big job, right? So some people, when their exams were going on, there will be like a group of people whose job is to actually provide the answers, okay? Yeah. So let me tell you, okay? So there were people who were trying to take the exam, and there was support cast outside the examination center whose job was to provide them the answers. Right? And there were so exam was of mechanical engineering, but by mistake, the person got a civil engineering answer. And that person actually wrote the civil engineering answer to responding. Then later that guy said, hey, Frank, what did you do that? You can't even solve the problem? Oh, I actually made a mistake. Go to the other guy. I gave it to you. My goodness, you need to understand that much. Okay, so the rest of it, so once we created the data set, now we have to look at, okay, some properties of this variable that we have created. How many zeros are there? How many ones are there? Okay, so there are, now it is looking at, there is a command, so we are looking at sum. It's just giving the number of observations, which is, then the mean is 0.11. Tabulate that we're looking at each unique values and how many observations are there. Okay, so when you did that, it's been giving me. So it is telling me also, just so that I don't forget what the variable is. So it's data remembers that. Okay. That you made it up, you just recoded it, okay? It remembers that. It is telling me it is a recode of innovation that was the original variable so that you don't get confused where it is coming from, okay? Because it's a recoded one. So, this one has 10,000 zeros and 300 ones, okay? Now the problem is to, okay? So now let's do the modeling part. So it's a very simple model. This problem is tailor-made for logic regression. So we are going to do that because we were trying to, so I had a tool, I was looking for a problem, okay? So like you have a hammer and you are looking for a nail. So I had the hammer, I was looking for a nail. I built a nail, okay? So sometimes we don't have work, so we create work. So this was like that. So I don't have problems, I create a problem for myself so that I can solve the problem. So it is simple. We are looking at the logic. Innovative is the variable. And I'm just kind of thinking, still trying to make some sense. It's a random thing, okay? But I'm just putting, okay, R&D, because we had a variable that spending, but that there is nothing to do with the real R. But in that one, it is telling that it's an R&D, and I had a dichotomous variable firm size, which was a continuous one. Say I used this one to create a dichotomous. The purpose of that was to actually do an variable and to illustrate the point. Okay, remember that it's not an advice to you to do that. Okay, but to actually create a situation where I will have an interaction between a continuous variable and a categorical variable, and see that how we can actually look at and how to examine their interaction and interpret the information. We did it. So original one, there is no interaction here in this particular, but maybe. So we just let R&D and all of these the form size has 3 levels. Okay, so it's a 1, 2, 3. But in this output, you only see 2 and 3. And why don't you see the 1? That's the base level. Okay. Sometimes you can choose which level you want to make the base level. So in comparison to base 1, the effect of 2 is this. Okay. In comparison to 1, the effect of 3 is this. Okay. So that's the, so sometimes the theta will automatically choose a base. But if you want to know, okay, so you have a categorical variable. Okay. Say you are looking at race. Okay. You have black, white, Asian, whatever other possibilities. Okay. And you want to see that, okay, in comparison to, let's say, you want to choose the Asians as the, let's say, the base model. Okay. So in comparison to Asians, how the white is doing, or black is doing, or Latino is doing, but that's just a choice. In sometimes it makes the sense which one it be base, and sometimes it doesn't matter which one is base, as long as you know that there is a base level and the interpretation is based on that data set. And you see here that I have put the y variable as a predictor, which used to be our dependent variable until the last model. Okay, it's not that something I'm trying to tell you that, okay, this is what you should be doing. It's just I needed a variable to actually predict, and there was a built-in relationship, so I knew that there will be something coming up here. So you can see the firm size has no significant impact, but the R&D and the performance has impact on the probability of a firm becoming innovative. Okay, the way we defined innovation and innovative. So the probability of like becoming one is going to be the impact. Okay. Now, how to interpret the coefficient? Because you remember I said that the interpretation of the coefficients is not the way the interpretation happens in the linear regression. The interpretation is very definitely know that. But now this one is not that simple. So how it is interpreted? Okay. So the original model was the log of the odds ratio. Okay, was equal to the xb. Okay, so if you raise to the exponential, so on the left side will become the odds ratio, the right side will become exponent e to the power xb. Okay, so now x was, all the x's were many variables, okay? The x is a matrix, okay? So there will be x1, so e to the power x1 b e to the okay? So you multiply those two, get added up if you want to write same base, okay? Those are some very basic thing. I'm not going to get there, but it's the interpretation. So the interpretation of is, let's say there is a variable xi, okay, whose coefficient is beta I. You have already stated what is the beta I. Now you know the value of the beta I. So the interpretation is that, okay, if that xi changes by 1 unit, okay, so 1 unit change in xi will, in a multiplicative form, impact y, odds ratio. Y is here the odds ratio, okay? So it will impact the odds ratio by the beta I, okay? Do you follow that? So that's why it here, because this is not straightforward, okay? So, but I definitely expected you to know how to interpret the, in a linear regression, beta I. Obviously, this is, maybe you have done it, not done it, but if you have not done it, that's fine, okay? Yes, yes, so I just wrote it there. Can you see that? Read it. So, in the linear regression, it is an additive form, okay? So, here, a 1 unit change in x1 will change y by beta 1, okay? Will change y by beta 1. If beta 1 is positive, it will increase y by the amount of the beta 1. If the beta 1 is negative, it will reduce y by that value beta 1. In this one, the increase and decrease is being multiplied, okay? So the beta is more than 1, then the odds ratio is going to increase. If the beta 1 is less than 1, so if you multiply anything with less than 1, it's 0.9, so y, the odds ratio becomes 0.9 of what it was, okay? So it means the odds ratio is decreasing by that, because now it was 1, it became 0.9, because the beta 1 was 0.9. So I multiply that with that. So now the odds ratio, okay? So it's odds ratio means the odds ratio of that event, okay, will change. It will become now 0.9 if the beta 1 was 0.9. Follow that? This one, you see, is the same regression output with one change, and showing some slightly different numbers. Let me show that again more time, okay? So you look at the first one, this one here, okay? Observe it carefully, okay? So like in our childhood games, we're going to, okay, match, find the difference between two pictures, okay? So that's the problem you have got. Find the difference, okay? Look at this one for 30, it's a KBC problem, okay? Going to send the next one, okay? What's the difference? There are many differences, okay? But so there is, and the command is here, which is asking us to report the odds ratio, okay? So these numbers are now actually are being reported in the e to the power xb part, e to the power b part, okay? So they have been now reported. So now you can actually directly interpret that the impact 1 unit change so it is the odds is increasing by 0.64, okay? Because it's more than 1, and how it is more than much is 0.64, it is more, okay? So the odd of 1 point, okay? So here all the numbers are more than 1, okay? Except the constant, okay? So all the numbers are more than 1, so we don't have a negative thing. But if it was a negative, so then there won't be a negative coefficient here, okay? How the negative will show up? Let's say there was effect of a variable and impact of the variable on the odds ratio. But what kind of number it will show up? It was a negative then? Less than 1. So you will know if it is more than 1, it is increasing the odds. If it's less than 1, then it is, and it's less than 1 will be actually more than 0. Okay? So it won't be a negative here. Negative will be, if it is less than 1, then it is negative. It's more than 1, it's positive. Okay? Because I converted them to the odds ratio. So now it is, and you know the interpretation of that as well. Okay? Everyone with me? Fine? Okay? This one I wanted to explain. Okay? I was not hoping to explain that one. Okay? Because I knew that you probably know if you're doing all of that. But this one, maybe you have done it, maybe not. But people come from different areas. You have done a modeling, logistic regression, or may not have done it. But that's why we are here, okay, to do that. But not for that one. Now, if you look at, we want to see that if there is this model, okay, how good is the model? So we actually do a change in, there is a likelihood ratio number. Anytime you want to see that how good is the model, so you want to see a base one and then comparison to the other model, 2 models to change, look at the one. Okay? So the other one is just the constant. Okay? So there was no predictor in the model. So I only had a dependent variable and I asked it to run. So it means it has only constant. Let's say if you run regress y, okay? So it is going to only say constant. Okay? There is no other x there. So there is no one. Okay? So I'm using those 2 differences. Just trying to show you the difference that how much, including those variables that we included in the model, that how much it is making the predictions better. Okay? So in order to do that, we are looking at the way we do it is 1 minus. So it is reporting a pseudo R square. Okay, if you go back, let me go back here. Okay. So you look at here, it is reporting a pseudo R. In a regular regression, we have R square, and you kind of look at the R square and the difference in R square to estimate that, okay, how much the R square is improving. So is it helping me to predict my variable better or not? Okay. But in a logistic regression, it is not reporting R square, it is reporting pseudo R square. It is calling it pseudo R is why it is R square. It is R square, they're calling it because it has a somewhat similar interpretation, and they put pseudo on top of that because it's not R square. Okay, but how it is computed. So I just wanted to kind of help you see the math part, because the table is showing that. Okay, but I wanted you to know where it is coming from, like what is the meaning of it. Okay, so in order to do that, I just kind of did this part here. So first model that I ran, okay, I just copied. You see here, there is a log likelihood value here. Okay, on the top here, it is showing the log likelihood, the value there. Okay. So this one is the log, and I did the same thing with the previous one, which is so I'm just copying this value. Okay, so this is my full model with all these predictors. This is the log like that is on that. So I just copied it, and now we are going to do the computation. Okay, so in the full model, the only model, this is the value. Okay, so the way pseudo R square is computed is 1 minus the log likelihood value of the full model divided by the log likelihood value of the constant only model. Okay, you always likelihood is reported and it shows up with a negative number. Okay, but because both of them are negative, so that negative sign did not matter for us in this case because they were both negative. And anytime you see, look at like two models just by looking at it. So if you see the log likelihood becoming less negative, that means your model has improved. Okay, just like you cannot intuitively look at the R square, and if the R square is more, then you see that, okay, maybe this model is explaining more. Okay, so if you just look at a model, you're looking at maybe comparing 2-3 models without doing a formal test, but just trying to get an intuitive sense that, okay, what it is. So if you see the log likelihood value becoming less negative, okay, so it is a negative, but becoming less negative, a smaller negative number is showing me, indicating me that it's an improvement in predicting that. Okay, so now you can do your own calculation here. Still see it, but I just did like a little bit of the calculation here. You will see that this is the pseudo R square here. That's what we were kind of thinking about. Okay. Now, so that's a pseudo R square. Okay, it's actually not the real way to interpret a logistic regression. Okay, to understand how good is my model. Okay, so in order to understand how good is my prediction, there is another which we do, and I'm trying to explain to you here. Okay? We had, so let's think about, okay, so we had 1 or 0. 1 was the one that we called innovative, so it said yes if you are innovative, so those were ones. And the zeros what if you are not innovative. So let's say yes and no. If in another case somebody died, yes, somebody 0. Okay? It sounds like funny that, okay, died is 1 and like alive is 0, but that's how it is set up. Okay, so likelihood of occurring the event is the 1, okay, which is considered positive, but death is not positive. Okay, so but it's how we are going to treat it. Right? Okay. So what we are looking at is, in order to know that whether my prediction is right or not, if I can predict every company here in this case that was 1 or innovative, if my model predicts it that it is innovative, okay, then it will be right. Okay? If everyone originally 0 means not innovative, and my model predicts it that it's not innovative, then if I get all of those correct, okay, every 1 as 1 and every 0 as 0, my model will be predicting 100%, okay, equivalent to like 100% R square in a regular regression model. Okay, so I have the y's, and I'm looking at the predicted value of the y and comparing that and putting them side by side. What was my original observation? That this was alive, okay, but my model is predicting that that guy should be dead. Okay, so it's not right. Okay, this guy died, but my model is predicting that he should or she should be still alive. Okay, so there is a mismatch. So let's do this 2 by 2 cell matrix. Okay, so in the 2 by 2 matrix, on one side I have put here that the original case. Okay, so innovative yes and no. Okay, on the left hand side here I am looking at the predicted, okay, yes and no. And then we are looking at, okay, what was the original and what is the predicted. Okay, so if the original was innovative, predicted was yes. Okay, so I'm saying true prediction. Okay, TP is true positive. Okay, so it's a, we are looking at positive and negative, so it's a true positive. Okay, because the 1 was the positive event. Okay, so it's a true positive. So the event, the observation was 1, and we predicted it 1. My model predicted it 1. The second one is that the original was no, but my model predicted it actually 1. Okay, so it's a false positive, FP. Okay, false positive. that I am actually declaring something of happening while in reality it did not happen. So I'm predicting somebody or to be like benefiting from a medicine, and the person did not benefit based on my criteria. Weight and did not lose based on right. Okay, so I'm looking at so that's a false positive, that it was actually no, but I said my model is saying it yes. Okay, it's a false positive. The second row is the predicted is no. Okay, so if the predicted is no, but the original was yes, so it's a false negative. Okay, so let's say you have a quality control you are a quality control manager in your company, and you are looking at whether this product is defective or not. Okay, and you are categorizing that. Okay, so this is defective and this is not defective. Okay, so this is the one you are actually saying these are defective ones, but people actually found that what you call defective is actually not defective. Okay, it's a false negative, that you mislabeled a product that originally the product was good, but you called it a no, it's not good. And then last one is that the company was not innovative, it was no, and you predicted no. Okay, matching. So it's true negative. Okay, so TN is for true negative. Now, in many cases, let's say you will find that the positive event happening is a small fraction of the data in which actually that event is occurring. Let's say you are looking at accident, okay, or death or birth or something in a larger population. So you will see that the proportion of one is actually smaller in a real data set, but here it's not that way as much. But in a real one, you will find it's a reverse situation. Okay, the ones will be smaller and zeros will be large. Okay, so that's like people dying. Okay, you're observing them with a like 10-year period, taking medicine. So the people who are dying are a small fraction. People who are still alive is large. So let us a small one and zero. Now, if you are a model, let's do a modeling, and you said that okay, I'm going to call everyone as zero. Okay, think about situation. Okay, say I don't care. I'm going to predict. I write a model. Okay, and I will say everyone will be zero. You still get a pretty good hit rate because you will still get all the people who were zero. You got all of them. Only a small fraction, those were actually ones. You call them zero, but they were one. But they were a small fraction of your model. You'll still get a good hit rate, isn't it? Okay, your model, you'll say that if I just take a position, okay, because I know the event that is happening is a very small fraction. The event that is not happening, the zeros are a large number of zeros. Okay, so I call everything zero, or the reverse way. Okay, if the situation is that a lot of ones and very small zeros. Okay, so my default will be I call everybody one. Okay, there will be some zeros in that I'll get wrong, but it's a small fraction. My predicting power, if I go by R square, pretty high. You get my point? So we cannot use that style of prediction here, right? Because I'm just taking one side, prove my predicting power. So I'm just not bothering about the other possibility. I'm calling everybody either 0 or 1. And I'll get some fraction wrong, but it's a small in my fraction. And it's my predict, like the R square will be pretty good. So that's why this scheme came. Okay, my model will be good if only it gets these one right and it gets these one. It doesn't get this one and those two ones. Okay. True positive, false positive, and false. Okay. Have to minimize those. Okay, and I need to maximize true positive and true negative. Okay, those two diagonal cell observations. Okay, and the other diagonal I have to minimize. Okay, so only if I have a model like that, then I can say my model is good. It is predicting most of the positive, the true positive as positive, and most true negative as true negative. Okay, So then only I can say, yes, I have got a good model. Otherwise, if I just go by R square, I'm calling everyone one cell. I don't care about the other. I still get a good hit rate. Okay. So that's how there is a Navy history for this word, but it is called receiver operating characteristics. Okay, it's called ROC. Okay, so that's the name for this curve. So you see there is a curve here. Okay, and it has specificity. When I plot this, the curve, okay, if my model is stable, okay, so that value is absolutely the ROC value would be 0.5, okay, just like tossing a coin, okay. Two outcomes. I'm taking a middle position, so that will be my baseline. Okay, as worst as I can get is 0.5. So now the difference is how much my model is improving, that how much more I am going on top of 0.5. Okay, and I can go maximum is 1. Okay, so this is where we kind of area under the ROC curve here. Okay, yes. For this particular model that we ran, okay, the value was 0.86687. Okay, you see here the value. Now this is the curve. Goes to straight line, which is a diagonal, closer to 0.5. And if it goes towards the outer here, it will go to, okay, follow me on this. So this is the number we should use to interpret a we look at the it's a of fit, okay, the goodness of fit measure equivalent to that instead of using the, so we did the pseudo just an intuitive one, but this is the one that we should be looking at when you are some paper application showing that any of those it or not. Okay, the reason many people don't do it because they know it. Okay, that this is how and do it. Okay? And, okay, calls everyone either one or a square. Okay, or square. So let's do some more. Let's skip a few, which is kind of similar kind of style with the probit regression. Slightly because we're talking a variable, dependent variable can multiple values. Okay. .876. And is for that LROC. Okay. So if you after model. And it will give you that curve. Okay? Yeah, thank you for asking because that's what's important. Sure. So we are looking at a dependent variable, which we call a discrete variable, or it is taking only 0 or the positive integers. Okay, there is no negative number it can take, and it cannot be an intermediate. Okay, like predicting the number of children a family has. Okay, so it could be 0, 1, 2, 3, or whatever, but it cannot be anything in between. It cannot be negative. Okay, so you can visualize that kind of situation, that the minimum it can be 0, and it can only take integer values. Okay, so this is the kind of situation. Now we want to model that variable that we are trying to predict. Let's say in this case, I had created in the originally a variable which we used to use the 15 number to dichotomize. Okay, so that was the original innovation 1 variable. Now we are going to use that one. Okay, because that one was that. So now it's going back to the original one. That okay, we're not going to dichotomize it. We are going to model it as it was in this made-up data set. Okay, so data set I had by choice I had done it that way. Okay, because I wanted to use the one data set and probably utilize several models. Okay, instead of trying to take different pieces coming from different parts, some of them are loading or not loading. You are free of all of that. Okay, it's your do file. You build the data set. You change it. You make it the way you want it. You run it. Okay, you don't need anything from outside. So that's and you can see how good is your model because you are making it. Okay, so you know what's the value. It follows what we say, the probability that event that is happening, it takes a particular value. Okay, so what is the probability a family is likely to have 2 children, okay, or a family having 4 children? So we are looking at, so it can have those numbers, and we are looking at which we are interested in predicting that if that event taking a particular value. So in this case, we had the made-up data set was a patent was we just gave it a name because patents could be 0, 1, 2, 3, 4, and we are looking at, okay, in this model, what is the probability of a firm getting H patents? Okay, so H could be a number 0, 1, 2, 3. So the formula is that it is E is for the exponential to the power minus mu multiplied by mu to the power H. Okay, H is the probability of that event taking the value of H, okay, divided by factorial H. Okay, so I mean, I don't know which way you write, but back in our days we wrote the factorial 2 ways. Okay, you could have an exclamation point, or you can write this way. So I don't know, I'm an old guy using that, but it's what it is. It's a factorial H. Okay. Now, so if let's say start with the base of patents. Okay, taking 0. So if you in that E to the power minus mu to the power 0 divided by factorial 0. Okay, so factorial 0 will become 1. Okay, anything power 0 becomes 1. So this becomes E to the power minus mu. Okay, because I didn't talk about what is mu in that. Okay, so the mu this one is the expectation, the mean expectation. Okay, that of event, it is going to take E to the power xb. Okay, we follow that xb logic. So it's all predictor variables in the matrix form. Okay, so all the x's are captured in this matrix form, and mu is the mean, the expected mean value is E to the power xb. Okay, so the regression that we are going to use first, it's a very robust technique. Okay, it only needs that conditional mean information. As long as that we get right, it can do a pretty good job of predicting. That's the only piece of information it needs to do its job. Okay, Do you follow that? Yeah. So let's written in a mixed language. Got it? Okay. So that's how it is represented here. Okay. Now, what are the is making? Okay. So Poisson makes one assumption. Okay. The assumption is the equality of the mean and the variance of the event. Okay. So they are equal. That is the assumption it is making. Okay. That the event that you are looking, let's say the number of children occurring in the society, you're looking the mean number of children in the society, and you are looking at the variance. Okay. So it is assuming that the mean and the variance of that variable are equal. That's the assumption model is making. Okay. Now, derivation of like likelihood method, okay, one is making an assumption that the mean is proportionate to variance. Okay. So it's not equal, but you can model it as a proportion, and the proportion is here we are. Okay. You see here this part. Okay. So here the sigma square I added multiplied this one with a sigma square. Okay. If sigma square is equal to 1, the sigma square is less, okay. If sigma, it is a situation where it's called over dispersion. Okay. So three possibilities. Okay. It's Poisson, or under dispersion, or over dispersion. Typically, as many events that has under dispersion issue, but we come across situations where a lot of over dispersion happens. Okay, and there is a technique to address that situation, which is called the over dispersion. Okay. Running the model now, the Poisson, okay, and usually that doesn't take much time. Okay, so all you are doing is replacing and putting the word Poisson. Okay, variable was innovation 1 that was in the data set. Originally we had it. Okay, I am creating an interaction. Okay, now you see here I have put 2 sign between R&D and the firm size. Do you see that? Previously I had 1 pound sign. Okay, in this one I put 2. What exactly I'm trying to do? Did you notice the difference? Okay, so in the previous interaction I had 1. Okay, and I put it 2 here. Not exactly way of writing a longer command, but one. Okay, so you two variables, we should have those variables should be in the model on their own as well. Okay, so let's say we have a modeling R&D and firm size should interact. Okay, then we should have R&D itself and here I just wrote R&D and firm size. Okay, I didn't write R&D separately. I didn't write firm size separately. Okay, but Stata knows what I am doing, what I'm asking it to do by putting an additional pound sign. Okay, so it is taking my command, it put it by itself, it put the firm size by itself. Okay, the the interaction between firm size and the R&D. Okay, so it's just a short way of independent values as well as their product in their model. Okay, so I can write those separately, or I can just use an extra pound sign. If I don't use the extra pound sign, it will only include the product. Okay, it will not include. I have to write those. Okay, the R&D and this. By doing this, I never make a mistake of forgetting to not putting the original by itself. Okay, so by default it will put it because I'm following this, and as a discipline, every time I do, I'm just going to do it the same way, so it doesn't make the mistake. Okay, so now we see the here as positive firm size. The variable is 1. In comparison to firm size 1, 2 does not have a significant impact on a firm the producing or becoming innovative. Firm size 3 has, in comparison to 1, has positive. Okay. 3 is so you can see the models. I'm looking at these firm size. I see here this one has significant impact, and I see this particular one in comparison to the level significant impact. I put Y as and R&D itself has a significant impact. Okay. Now the thing I wanted to show you is how to plot an interaction graph. Okay, because it's complicated. You don't know what is the impact of what is happening, right? How firms, how to interpret that information, because they're appearing at several places. Some of them are significant, some are not, and their values are different. There is no way we can play that table. The only way to interpret that information is actually graphing it. Okay? So once we graph it, then it becomes clear what is here, that the firm size 1, 2, 3, all 3 of them show up in the model. Okay, the graph. There are 3 lines. Okay, each line corresponds to one of those 2 firm size. Okay, so firm size 1, 2, and 3. Okay, 3 colors, 3 of those firms, and then we have the variable R&D. Okay, so R&D is changing. I have changing from 3 to 13. Okay, the R&D here starting from 3, going all the way until 13 with an incremental value of 1. Okay, so in my axis I should have 3, 4, 5, 6 until I hit 13. Okay, which was the maximum one in my data set, in the made up data set. Right. So you see here the command margin. I given incremental value of 2. Okay, it will just have fewer data points. I could have given incremental value of, let's say, in this case doesn't make sense, in some 0.5, okay? But this one is an integer, so it doesn't make sense to give a incremental value less than 1, because it can only increase by 1. That's the minimum. Okay, so points should be meaningful what you are getting. Okay? Okay, and I said that I wanted to interact a continuous variable with a categorical variable. Okay, and that's why I created a new variable firm size, which was originally a firm sales, which was a continuous variable. I forced it to create a categorical variable, a small firm, a medium-sized firm, and a large firm. I said 1, 2, 3. Okay, 1 is the small, 2 is the medium size, and 3 is a large. Okay, it's possible that you can have a sales and you can say, okay, these are the small ones. These ones I'll call medium. These ones are large ones. Okay, so let's just try to create that situation where I have these 3 levels of firm size, interacting firm size with the R&D expenditure, that how many money they are spending and what is the innovation they are generating. Okay, so innovation here, the values are starting. If you look at the numbers, are minimum numbers are 10, 12, 16, and 18. Is this axis on the left side, you will see that what are the values we are looking at. So minimum it is looking at 10 in this range, and the maximum is 18. Okay, so probability of a firm producing 10 patents, 12, 14, 16, and 18. That's one. Okay, you see that the green line is the one which is the large company in this made-up data set. Okay, so we are seeing that the interaction between the R&D expenditure, the money a firm is spending, the large firms are actually benefiting less than the medium and the small firms. Okay? So you see here, but we don't see a significant difference between the medium size and the small size. Why? Because the confidence intervals overlap. So anytime you see the confidence interval, so it's very important to include the confidence interval. Okay, so because confidence interval, we can see that there is no significant difference between the money the medium-sized companies and the small companies are doing. They are benefiting more or less similarly. While there is a trend that the smaller firms are actually benefiting the most, but there is no significant difference. Okay, so you can see the blue line is showing up on the top, the brown line is in the middle, and the green is in the between. Okay, and you can see the green is the confidence interval of green does not overlap with any of the blue or the brown. Okay, which is telling me that this one has important that when you are doing this kind of like interaction in a non-linear model, nobody should interpret the coefficient directly. If you have an interaction, then you need to actually graph it, and then you can see parts of the curve. Okay, like there may be like situations where the green is also not different. Okay, on this side the confidence interval is overlapping. Okay, even the green parts. Okay, but the confidence interval in this part is not overlapping. Okay, but on the very low side, all three are in overlapping. What does it mean? You have to write it in terms of interpreting and communicating the information, that when the firm R&D expenditure is on the lower, okay, in the range from 3 to like 6 or 7 in this unit, there is no significant difference among the firm size and the they're not getting anybody better benefit. Okay. While the interaction is negative, but there is no significant difference because the confidence intervals overlap, which means it can be in among those. So low could be there and high could be in that. So when it's an overlap, it means you could be anywhere in that confidence interval. So that means there is no significant difference. If I don't have the confidence interval, then those lines, the gap will actually become wider. The graph will look nicer if I don't put the confidence interval. And when you can do a negative binomial regression. Okay, so when the mean and the variance equality condition is not met. Okay, you remember we said that the Poisson is making that assumption, and I said when there is that assumption is violated, we have a technique to address that situation. To address that situation, we use a technique which we call a negative regression. Okay, so now you follow that, and when we are using the one that you were talking about. Okay, some kind of parameters. It is looking at a slight, an offset. It is treating that as if the variable is there is a miss on assuming that it is a pattern. It's a gamma distribution with mean value 1 and a dispersion parameter alpha. Modeling the same kind of situation using a negative binomial regression. That the negative binomial regression is assuming that there is a missing not equal. So that's here we can just make the same change and just make the NB reg. The rest of the stuff is very similar. It just you need to look at here. So I said there is a dispersion parameter alpha with a mean gamma distribution. 9 how important or unimportant you saw the you can see that it's -10. It's 0.00, keep going, so it is almost 0. So in this, right, there was no over dispersion problem. Okay, so in this one, which we were not able to create a situation where there was also a dispersion, over dispersion problem, and it okay, is reporting the test here, the likelihood ratio test at the bottom. It is looking at there is an over dispersion or not. Okay, so when you run the negative binomial regression, the Stata itself is running the test for you, reporting the coefficient and formally testing that it is 0. Okay, so the bottom one, I just kind of did another problem. I'll stop.